Okay, let's continue our discussion of differential cross sections or cross sections in general. Okay. Fine. So let's recall what we wrote down for the cross section. It was this expression here. I'm just rewriting it. It will be useful. So d sigma, okay, is 1 over 4. I hope you have already done this exercise. I gave it last time. Minus 2 square. So we have some scattering happening, and these are the incoming particles of momentum k1 and k2. Okay, this beam had momentum. I think I called it k1. So I should label it like this. Okay. So then you have all these differential elements. These correspond to the final state particles. Okay. Then you have matrix element squared. I will suppress the arguments, and then you have, I should also this k1 plus k2 minus summation over pi. Okay, this delta function also times matrix element square. Okay, and right now all the differential elements p1, p2, pn, they are in different regions. They do not overlap. Okay. So one thing I forgot to tell you last time, I realized later that I didn't mention. So here, here till this stage we had this probability given by this expression where we had f1 tilde and f2 tilde still present here, and after that I used the normalization of f1 tilde and f2 tilde which I had shown you earlier, and I was assuming that, I was working in the limit in which these folding functions or smearing functions are sharply peaked around values k1 and k2. Okay, so that only those values are picked up by these factors. Okay, and this is no problem, because even though the width of these Gaussians which we are taking as smearing functions, they are finite, they are not zero, something small. Okay, but that doesn't cause any trouble, because if you look at detectors, okay, when they detect a particle hits somewhere and they can detect the momentum, but they detect the momentum with some finite resolution. Okay, they cannot distinguish between a particle which is having a momentum sharply peaked at k1, or if it has a small spread around k1. Okay, so when you prepare these states, our measurements are not of that quality that they can really resolve the difference between a very sharp peak and a slightly broad peak. Okay, so we are not making any error in that sense. Okay, so these are all consistent with the measurement requirements that we have. Okay, so I can replace these by their just normalizations, and I'm assuming that I have a very sharply peaked Gaussian. Okay. Also, some names I want to tell. So look at this factor. This factor has come from here. This line here, and of course this is not a Lorentz invariant quantity, but what you see in this line, it is boost invariant along z direction. If you do boost only along z direction, then it doesn't change. And I can so this object, you should not think that this is Lorentz invariant, even though the way it is written it is Lorentz invariant. But then we should understand that this line is equal to this factor only when k1 and k2 are parallel to each other. Okay, they are collinear momenta, not otherwise. Okay, otherwise this is not equal to that. Okay, so it is equal only if only in that limit, this collinear limit, where these k1 and k2 are along the z-axis. Okay, then so that's invariant under boost along z. But other than that, all other factors are invariant, Lorentz invariant. Okay, so if you look at this kind of things we have seen in the first course also. Okay, this is just invariant measure. Similarly, these are all invariant. This is anyway delta 4, so that's invariant. That matrix element squared is also invariant. Okay, so other than this factor, everything else is Lorentz invariant, and this piece is invariant under boost along the z-axis. Okay, another thing, that if these regions R1, R2, Rn, they overlap, okay, and because we are going in this theory we have bosons, identical bosons. Okay, so the same state gets counted twice, right? Because if you have two particles in a given region and the regions overlap, two particles in a given region, then saying that this one has momentum p1 and that one has momentum p2, or vice versa, these are not two different states. This is the same state, right? You can these particles are indistinguishable, but the way this has been set up, okay, it is counting as if these particles are distinguishable. You are tracking the momenta of each of these particles. So I will be then overcounting the number of such states, and I should divide by 1 over 1 factorial, n factorial, if you have n particles in the final state. Okay, so divide by n factorial if the regions overlap, if all of these r's are same, identical. Okay, and then that factor you can include together with mod m square. So you can write 1 over n factorial mod m square. That will be the case when you have identical particles. Okay, some names. This factor is called flux factor. This first prefactor is called flux factor. That's just a name. It's useful to have names so that you can refer to these objects easily. Okay, that's flux factor, and you get total cross section sigma if you integrate over the entire phase space. and this thing is called phase space. Okay, if I integrate over these integral dp1, integral dpn, okay, with these objects together with the delta function, that is called phase space. I will write down in a moment. If we integrate over the entire phase space. And what's phase space? Is integral d cube p I over 2 pi cube 1 over 2 omega p I product over all I. So this entire factor times 2 pi to the 4 delta 4 okay, this entire thing is called phase space, okay, or phase space integral. Phase space. So because it is Lorentz invariant, it is also called Lorentz invariant phase space, ellipse. Okay, and the differential elements are sometimes called d-ellipse. Okay, good. Then let's look at some examples. So first, let's one body. Look at first a process which has one body final state. Okay, this will be useful when you are studying deep inelastic scattering, and we will not do that in this course, but at least I can talk about phase space here. So here is the thing. So you have a particle with momentum k1, another particle with momentum k2, and as far as I am concerned right now, it doesn't matter whether what is the nature of these particles, okay, because I am looking only at the kinematics, the phase space part. Okay, I am not looking at the dynamics. Dynamics is contained in mod m square. That guy knows about which particle is interacting with which kind of particle and what are the interaction forces, but phase space doesn't know about those things. So suppose we look at one body final state, and then I want to write down the expression of cross section. Of course, I will write it in terms of mod m square. Mod m square I will not specify because that requires looking at a particular process, but I will do the kinematic part. And I will also allow for these masses to be different. So let's say this particle has mass m1, the momentum k2 is carried by a particle of mass m2, and this p is carried by a particle of mass m. So what's cross section? Cross section is flux factor times integral over the phase space times matrix element square. Okay, so let's do the phase space first. Okay, phase space, let's write it as d pi 1. That's just the notation for this thing. 1 stands for one body final state. Okay, so this is integral d pi 1. That's what the notation is. So d pi 1 is equal to, what is that? D cube p, there is only one particle in the final state, 2 pi cube, okay, 1 over 2 omega p, where omega p is the energy of this particle, p, carrying momentum p, and then you have this delta function. Okay, I will encourage you to do this calculation before watching the video, and hopefully you will succeed on your own, but in case you have difficulty, then you can refer to this video. Okay, but try it on your own first. Okay, so this is Lorentz invariant object, and we have seen earlier that we can write this as d4p over 2 pi to the 4, then delta plus, and the plus means that the energy component is positive, delta plus of p square minus m square. Okay, and there is a factor of 2 pi that I am missing. 2 pi times delta plus of, something has happened again, now all the factors are fine. I am still missing this 2 pi to the 4 I think I know what is happening. P. Okay. Now because we have this K1 and K2 as these incoming particles with real energy, so they are positive automatically, so I don't have to write it as an additional constraint. Okay, because K1 plus K2, the energy component of this is the energy component of P0. Okay, and because K10 plus K20 is positive, P0 is positive. Okay, so it is ensured by this, so I don't need to carry a plus with me, I can drop it, it is automatically ensured from here. Okay, and then I can do the this integral d4p. Okay, by cube, sorry. So what will that give? It gives somehow factor of 2 pi 4. Sorry, that's the mistake. That's why my factors were not matching. 2 pi 4. So this 2 pi to the 4 cancels 2 pi to the 4, and only this 2 pi is left. So 2 pi. Okay. In doing the integral, we'll take away this delta function and replace p by k1 plus k2. So I get k1 plus k2 whole square minus m square. Okay, that is fine, that is good. So sigma cross section is now pi over 2 1 over k1 dot k2 whole square minus m1 square m2 square times this delta of k1 plus k2 whole square minus m square times matrix element square. Okay, so this will be the expression, and you can now, for whatever process you want to get this cross section, you can supply the mod m square for that process, and this line will provide you the result for that. Okay, so next we will take a two-body final state. Okay, so let's look at two-body final state. Okay. So what's the phase space? That's I'm going to denote by d pi 2. 2 refers to the two body final state. Okay, and the phase space is integral d cube p1 over 2 pi cube 1 over 2 omega. I want to write p1. So the energy omega p1 is the energy of particle carrying momentum p1. Then integral d cube p2 over 2 pi cube 1 over 2 omega p2, and then our energy momentum conserving delta function k1 plus k2 minus p1 minus p2. Okay, now this object is Lorentz invariant, as I have said earlier also. So let's go and evaluate this in the center of mass frame of K1 and K2. So let's evaluate it in K1 plus K2 rest frame. Okay, so K1 is equal to minus K2. So the momenta of incoming particles are back to back and equal. So if we are in that frame, and the center of mass energy would be omega K1 plus omega K2, which I will call omega Cm. Okay. Now, if I look at this delta function in the center of mass frame, then I can write it as, see, these are 4 delta functions. I will write energy, delta function corresponding to energy and the momenta separately. So you will have delta of omega Cm. So K1 0 plus K2 0 is what is omega K1 plus omega K2, and because I am in center of mass frame, this is equal to omega Cm, should be equal to omega P1 plus omega P2, right? This is what I should get. And then the delta cube of, now because of my choice, K1 plus K2 is equal to 0. So sum of these 3 momenta is equal to 0. And then I am left with only P1 plus P2. Okay. What does this delta function says? This delta function says that it hits only when P2 is equal to minus P1. Okay, meaning the momentum of the final state particles are back to back. Okay, it doesn't tell you the direction, but it tells you that they are back to back, which is what you expect. Okay, so momentum conserving delta function is giving you the correct result. Okay. Now, as I have said repeatedly, the moment you have delta functions, it's easy to integrate. So let's integrate over d cube p2, okay, and use up this delta function. And doing so, we will put p2 equal to minus p1 wherever p2 appears, okay, which is this place, 1 over 2 omega p2, and also this delta function. So these 3 delta functions will be used up, 1 delta function will be left, and all p2s will get replaced by p1. So what you get is the following. Okay. So 2 pi cube will kill this 2 pi, will leave only one factor of 2 pi from here, and you will have 1 over 2 omega p2. But now here in this p2 you should use p2 equal to minus p1. Okay, that's what you should do. But I will still continue writing p2, it's easier to write that way, but we understand that this condition has to be supplied, that p1 plus p2 equal to 0. Okay. then you have factor of 2 pi, and then a delta of omega cm minus omega p1 minus omega p2. And here also in this, so what is omega p2 now? Omega p2 was p2 square plus m2 square, but now that is, because of this delta function, p1 square plus m2 square, okay, because I put p2 equal to minus p1. So that is omega p2. Okay, good, that's fine. Now omega p1 and omega p2, they all contain p1 square, right? Now we still have an integral left over p1, but they all have the square of the magnitude of vector p1, right? Because p1 appears here and appears in this, exactly in this way, p1 square plus m1 square root. It appears here, again you have p1 square appearing here, and these two places also. Okay, so I can do this integral if I separate this into angular and radial parts, okay, and then I can use one of these this delta function, which is only one, and do the integral. So that's what I'm going to do now. So d cube p1 I will write as dp1 dp1, that's the magnitude of p1, then p1 square, okay, magnitude of p1 square, and then you have also the solid angle, okay. So this is what you have. This is the solid angle, volume element coming from the solid angle, and this is the radial part, okay. Now I will do this, do these integrals, or probably not yet. Yeah. So I can write, let's write once this expression, it will be useful. So I am writing d sigma over d omega, okay. So I am taking this volume element to the left side of this expression, right. So d sigma, I have calculated d cube p1, d cube p2, that thing, okay, and I have mod m square, and the final integral with d cube p1, I have a d omega, that d omega I am taking to the left, so I get d sigma over d omega, okay, and this is equal to 1 over 4 k1 dot k2 whole square minus m1 square m2 square, that's the flux factor, times integral dp1 over 2 pi cube, then you have p1 mod square, then 1 over 2 omega p1 omega p2, but remember p2 vector is equal to minus p1 vector, that is what I should use, 2 pi times delta of omega center of mass minus omega p1 minus omega p2 times mod m square, okay. So this mod m square has to be integrated over p1. Okay, so now we have to do the integral, and for that I will utilize this delta function, I should find out the measure it provides. So that's easy. So you take delta of omega center of mass minus omega p1 minus omega p2, okay, and take this argument and define it to be f of p1. What is f of p1? It is this thing, omega cm minus omega p1 minus omega p2, okay. Now I should find out the derivative of f with respect to the magnitude of p1. What will that give? This gives a constant, okay, and actually a modulus of this I will need 1 over modulus of this. So modulus of this is, this gives 0. This will give you, maybe I'll just write down the final answer because it's very easy. You will get p1 over omega p1 omega p2 times omega cm. Okay, you can do this differentiation, it's not difficult. Okay, so what do you get? Let's check. Let me write now. So this is 1 over 4 times whatever that is in the square root times, so this factor I have to divide in the denominator, so that will give you omega p1 omega p2, okay, over omega cm, okay, that comes from here, and then you also have magnitude of p1, okay. So 1 over this thing, fine. Then when I do the integral over p1, that delta function gets used up, okay, and yeah, here 1 over 2 pi cube okay, where I should use omega p1 plus omega p2 is equal to the center of mass energy, okay. So there is a factor of 4 coming from here, and mod m square. Let me check if I missed something. All looks good. So I'll write it down. 4 times that square root times 1 over 4 into 2 pi square into this 1 over omega cm, and then this p1 gets cancelled with this p1 square, so I have only p1 modulus square, and then I have matrix element square. Okay, did I miss something? No, everything is here. Okay, so now let's look at the flux factor. So this involves k1 dot k2 whole square. So let me first calculate that. So for that I will calculate k1 plus k2 square, and this is k1 square plus k2 square plus 2 k1 dot k2. Okay, where when I write k1 square, this is k mu. Okay, so k1 square is just m1 square, k2 square is m2 square plus 2 k1 dot k2. Okay, and we are in the center of mass, we are in the frame k1 plus k2 equal to 0. So this thing, the spatial components of this sum is 0 and only temporal components are there. So that is what I am going to use now. And this is just omega center of mass squared. Okay. So what is k1 dot k2 is k1 dot k2 is 1 over 2 omega cm square actually what I wanted to do was I want to take the case where m1 is equal to m2 is equal to also mp1 equal to mp2, meaning all the particles have the same mass. Okay, so I am looking at that case now. So this becomes plus m square, okay, because this gives you 2m square, and when you divide by 2 it gives you m square. Okay, so with that k1 dot k2 whole square minus m1 square m2 square, which becomes m to the 4, that square root we need to calculate, and this object is equal to, I will just substitute here, I will just skip some trivial steps. You can check that it should come out to be omega cm square over 4 minus m square. Okay, that is what you should get. And then you can use that omega cm minus m square. Okay, this you can check. Now omega cm square, that is the center of mass energy square, will be equal to the half of the energy of one of these particles, right? Because all particles, the incoming ones, they have equal energies, they have equal masses, equal momenta, so equal energies, and similarly for the ones going out, they have equal momenta of, the magnitude of the momenta is same, but they are also carrying equal masses, so the energies are also equal. So it is twice the energy of P1. Okay. So what I am saying is, your final state particles are going back to back because you are in the center of mass frame. The momentum of this guy is equal to the momentum of this guy. Okay. And because the masses are equal, the energies are also equal. Okay. Because E square minus P square is m square. So because m's are equal, E's have to be equal, or omegas have to be equal. Okay, so this is 4 omega P1 square. So it becomes omega center of mass square omega P1 square minus m square. And what is this? E square minus P square, that's m, E square minus m square, that's P square. And what is P? That's this. Okay, so when I look at the flux factor for this case where all the particles have equal mass is the square root of this, which is omega cm times modulus of P1. Okay, now I can substitute this in this expression. Okay, for 1 over 4 times the square root, and what is that? Omega cm times P1. What happened? omega Cm times P1. So that will make it omega Cm square below, and one factor of P1 will get cancelled. So what do you get? You get d sigma over d omega is equal to let me write it here. Let's write here. This is equal to this factor I said it's omega Cm P1 times 4, and there's some there's this 4 also, 1 over 4. Okay, so this 4 times 4 16 times 4 64, so 1 over 64 pi square. Okay, this omega Cm makes it omega Cm square. This P1 will cancel, so I will just cancel this one and write P1 and then mod m square. Somehow I should have gotten a mod. I have an extra P1. How come? So this should have been P1, not P1 square. Correct, because I forgot to take into account this piece. So this will cancel this one, so that you have only P1, and this P1 which I had will cancel this P1. Okay, so you get 1 over 64 pi square 1 over omega center of mass square times mod m square. That's d sigma over d omega. Okay, for a two body final state, when you are looking it in the center of mass frame. Okay, because we made this specialization to this frame. Okay, so something, okay, now I know. Something went wrong. No, nothing went wrong. So let me write down the final result again. For 2 to 2 scattering cross section, with all masses equal to equal, the differential cross section, okay, d sigma over d omega in the center of mass frame is 1 over 64 pi square center of mass energy. I'll just write ECM instead of omega, it's easier to remember, times matrix element square. And note that this one is not proportional to some delta function, as we had for the some things are not. Okay, it's not behaving very properly. So for the case of one body, we had gotten a delta function. Let's check. One body, the cross section was proportional to a delta function, which was ensuring that k1 plus k2 squared is equal to m square. Okay, but here you don't have a delta function left. But that's a useful formula to remember, and we'll continue our discussion in the next video.